Hi everyone, I'm Brighton, and about to be presenting first for y'all. So my project and paper is entitled Parallelized Spark Implementation of an Inequality Join Algorithm. So the paper that this is based off on was actually worked on by Nicholas himself. And it talks about something called ranked enumeration. It talks about data joins, so that can include like inequality joins, and then an elimination algorithm. And this elimination algorithm is it works with like inequality joins, right? And although it was designed for ranked enumeration, we can also use it for something we're more familiar with, which is like the fast counting algorithm that we saw in homework 2. So let's see a motivating example. So here in data log and in relational algebra, I just have this simple two relations. And if we want to do an inequality join, so b less than c, an easy way to count it, or like a naive way, would just be like doing like a nested for loop type of approach, right? So the problem with this, of course, it's an n squared algorithm. So we can use this elimination algorithm to help us. And how it works is it's an n log n time transformation. And in the end, you get this factorized relation, and it takes n log n space. And the really neat thing about this factorized relations is that it reduces this inequality join problem into an equijoin problem, which means that if you were to just join the vertices, the ones that you see in the center of the column, you're able to get the same output as the naive solution. And not only that, you can also use the fast counting algorithm after applying this transformation. So that's really cool. But how does it work? How does this transformation work? To understand that, you would need to understand something called the tuple level factorization graph, which is like an abstraction to like convert the relation into this DAG problem. Unfortunately, with the time given, I cannot explain this whole thing. It's really interesting. I actually have a lot of slides prepared for it, as you can see. But we'll skip to the elimination algorithm, which is called multi-weight partitioning. So it takes n log n time, right? But it actually produces a tuple level factorization graph, TLFG, of size n log n, which is really, really good. And I also have a demonstration here. I won't go through the whole thing. But the main thing I want to point out is that, well, first of all, it's really neat. Like it sorts it, and it does this like quick sort type of like partitioning algorithm. So it's able to like represent the join in only a few passes in this recursive fashion. So it does, this partitioning part is the one I want to highlight in particular because it's involved in the Spark implementation that I have. But as you can see, I have this demonstration here. These slides are in the folders if you want to check it out. Like I made a very, very detailed diagram of this whole thing. So, okay. And after you do the algorithm, then you get this really beautiful TLFG at the end. Actually, I removed some of the notes because after that algorithm, it gets pretty messy. And this is messy already. But if you were actually to look at this, you can see that if you look at all the paths from the left nodes to the right nodes, so for example, the 0, 1 tuple, if you look at the path to the tuple 2, 0, you'll see that that actually is satisfying the inequality join, right? So like 1 less than 2, if you go down another path, maybe you can see like 1 less than 4, right? So this TLFG here, as messy as it is, it can be it can be converted back into like a relation format, right? Into the equijoin that we want. So yeah, it's pretty neat. And so the Spark implementation. So now we're moving away from that single core algorithm, and so this is the part that my project actually works on. So we can use Spark SQL and PySpark to help us parallelize this multi-weight partitioning algorithm, right? And the key the key parts of it is that in this partitioning step at the very start, we can assign a key to each partition. So there's 3 partitions here, so we can give like a, I don't know, like 1, 2, 3, right? And then you can delegate those partitions to different machines or different cores, and they can recursively run multi-weight partitioning on their own algorithm, right? So that's like the key like shuffle that's happening here. There's probably going to be more shufflings happening, as we like group together, and also do the fast counting algorithm, which kind of has like this group by operation, right? But that's the key part. And each of these machines or cores will end up running are going to do this and have like their own local 3 relations, which is the goal that we want to do a fast counting algorithm. So, of course, as I'm presenting earlier, I'm not quite finished the implementation. It's going all right, but I already have my experiments laid out. So, in order to test that this parallelized implementation actually works, we can just do the simple 2-relation inequality join, right? With the straightforward phrasing of the query and just running count on it. And then for my next one, I would want to do the multi-way partitioning algorithm with just 1 core, and then doing the fast counting algorithm. And then the main one that I'm working on is the parallelized version, right? Hopefully that one is the one that runs faster than the other ones. And then for a last one is a performance analysis that does the runtime based on how many partitions are created. Because if you create a bunch of partitions, you might have to deal with overhead problems from having to shuffle all of that. So it would be interesting to see if there's like a sweet spot to how many partitions are created. But yeah, so there's a lot of directions this can go after this project is done. So I'm working on a single machine for this, but obviously Spark is like you can parallelize it in a distributed system. So it would be interesting to see that performance. And then working with this algorithm with multiple relations, different like join predicate types. So not just less than, what about like less than or equal to, and other types of predicates. And like conjunctions and disjunctions of predicates. And then there is an open problem for the multi-way partitioning algorithm itself, which is that if you want to do like B less than C, A less than D, a conjunction of inequality predicates, multi-way partitioning algorithm, we're not sure quite yet if that can be done. But yeah, that's pretty much it. So, yeah, any questions?
Can you return to the last page before the Spark?
This one?
Yes. So in the right side S table here, we have 2, 4, and 2, 5. Okay. So my question is why for the 4 on the right side?
2, 4.
Yeah. The 4, 0, 4, 1, 5, 1, 5, 2.
Okay.
So why for the 5 we only have 1 node twice 3, but for the 4 we create 2 nodes here?
Oh, okay. Well, that's in the really complicated demonstration that I showed you. I can show you a little bit. But the first step is like trying to like do this one big sweep. So you can see that the partition at the bottom has the Y3, right? And same with the second partition. They only have like 1 node each for the first partition. But when you start recursing into each partition, you might be adding some more nodes like this. So I think it was this one, right? So you see the Y2 here. I renamed the Y2 into Y2-1 so that like the join values aren't like mixed up. But that's why that one has another node in there. Because yeah, this one here doesn't actually produce any join output. More accurately, this TLFD would have a bunch of like these dangling like intermediate nodes. I just removed them just for clarity, and so that like you can see that these paths satisfy the inequality join. Does that make sense? It takes a little bit of like looking at it. I know it's really messy, but yeah. What else we got?
I want to say one thing quickly. I wrote it on the PDF for the presentations, but please ask questions. Any questions to the speakers, and if you are worried that maybe you will make them get a worse grade or something, the contract between us is that if you ask a question and let's say the presenter can't answer, doesn't know anything, it doesn't matter, they will not get a worse grade. So your questions are not affecting the grade of the speaker. Yeah. My questions might, but feel free to ask questions.
Anything else? Hey, what's up?
I guess when you're parallelizing all of this, are you going to have to essentially do all the breaking up the pieces of your tables to send to Spark, or is that something that Spark does?
Oh, so you already start in Spark with this like big the input relations. So I know it looks like a graph, but you can remember that Like this is just like any other like two relations, right? Like so 0 and 1 1 is one table, 1 0 2 0 is another table. But yeah, the TLFG algorithm right here it's just to like what is it? It like helps like represent the algorithm itself. Because like if you just arbitrarily put these join values, right? Like it's not going to make a whole lot of sense. So this TLFG helps a lot with like representing the like relationships between the joins and everything. So yeah, but everything is being done in Spark. It's going to start in Spark. It's going to partition into different cores, and so yeah.
And what about the number of partitions? How do you decide that?
So I think in the paper it's, do I have it here? Yeah, I agree. So I believe it's this, right? So it's like, it counts the number of distinct tuples, and then the paper recommends that you can, that you do, what is this? Yeah, right here. Square root of the, a ceiling of the square root of the number of distinct values. So for 6 distinct values, that would evaluate to 3 partitions. Now I think you can technically choose like however many partitions you want, and that in fact that's what I'm doing for my experiment at the last part. But this is like the most efficient, like this is like a solid, like efficient one to get the nice like size and time guarantees.
Other questions? Okay, let's move on to the next.
All right, thank you.